Nothing captures our imagination quite like the mysterious inner workings of our own planet. For centuries, we've gazed upward at the stars, but some of the most fascinating discoveries lie beneath our feet. Recent scientific findings suggest something that sounds like science fiction. Earth's core is leaking. This isn't just a minor geological curiosity, it fundamentally challenges what we know about our planet's structure, history, and future. Today, we're diving deep into this emerging mystery that's rewriting Earth's story. Earth's structure has traditionally been taught as a series of neat, concentric layers: crust, mantle, outer core, inner core, each with distinct compositions and behaviors. It's a model that served science well for decades, but geology is rarely so tidy. Recent discoveries have revealed that the boundaries between Earth's layers are more porous than we thought, with material from the deepest parts of our planet making extraordinary journeys to the surface. The first evidence of this core leakage comes from Baffin Island in the Canadian Arctic. In 2023, geochemists analyzing volcanic rocks from this remote region discovered something remarkable: abnormally high concentrations of helium-3. Now, helium-3 is extremely rare on Earth's surface. It's primordial, meaning it was incorporated into our planet during its formation 4.5 billion years ago. Most of Earth's original helium-3 has escaped to space over the eons because Earth's gravity isn't strong enough to hold onto this light element. Yet these Arctic rocks contain helium-3 at levels scientists didn't expect to find. This helium isotope has a unique signature that identifies it as originating from the core, not from the mantle or crust. Finding it in these surface rocks is like discovering a time capsule from Earth's birth. The implications are staggering. Material from the innermost part of our planet is somehow making its way to the surface, carrying with it chemical messengers from Earth's formation. How does this happen? The mechanism appears to be mantle plumes, massive upwellings of hot rock that rise from near the core-mantle boundary all the way to the crust. These plumes are like geological elevators, transporting deep material upward over millions of years. When they reach the surface, they can trigger volcanic eruptions, bringing core material along for the ride. The helium-3 discovery challenges our understanding of Earth's core as a sealed, isolated system. It suggests the core and mantle exchange materials much more readily than previously thought. And it's not just helium. Scientists have also detected other isotopes and elements that appear to have made the journey from core to surface, including tungsten isotopes with signatures that date back to Earth's formation. What's particularly fascinating is that this leakage isn't a recent phenomenon. It's been happening throughout Earth's history. The core has been slowly releasing its primordial gases for billions of years. It's just that we've only recently developed the analytical tools sensitive enough to detect these subtle signals. But helium-3 leakage is just one piece of a complex puzzle that's reshaping our understanding of Earth's interior dynamics. Another key discovery comes from the Chora Valley in eastern Turkey, where scientists have observed a phenomenon known as lithospheric dripping. The lithosphere is Earth's rigid outer shell composed of the crust and uppermost mantle. In certain regions, portions of this lithosphere can become unstable and begin to sink into the more fluid asthenosphere below. This isn't the same as plate tectonics, where large plates slide horizontally. This is more like drops of honey slowly falling from a spoon. In Turkey, researchers have documented this process happening in real time. Using a combination of seismic imaging, satellite data, and field observations, they've shown that a portion of the lithosphere beneath the Chora Valley is literally dripping downward into the mantle. The surface expression is dramatic. The valley is subsiding at measurable rates while the surrounding areas are being uplifted as the heavy lithospheric anchor detaches. This dripping process creates pathways for deep material to rise, potentially including core-derived components. It's like squeezing one end of a water balloon. Pressure in one area creates movement elsewhere. As dense lithospheric material sinks, it displaces hotter, deeper material that can rise toward the surface. Laboratory experiments have helped scientists understand this process better. Using silicone putties and other materials to simulate Earth's layers, researchers have recreated lithospheric dripping in controlled environments. These experiments confirm that dripping isn't just a theoretical concept, it's a physical reality that follows predictable patterns. What's particularly concerning about lithospheric dripping is that it can trigger a cascade effect. Once one region begins to drip, it can destabilize adjacent areas, potentially leading to more widespread geological activity. It's a reminder that Earth's seemingly solid surface is actually a thin, fragile skin floating on a dynamic, fluid interior. The concept of material exchange between Earth's layers isn't entirely new. In fact, it has a fascinating historical precedent that takes us back to the late 17th century. In 1692, the famed astronomer Edmond Halley, yes, the same Halley who predicted the return of the comet that bears his name, proposed a radical theory. Earth is hollow. Halley suggested that our planet consists of several concentric shells separated by atmospheres, each capable of supporting life. He developed this theory partly to explain anomalous compass readings, which he attributed to moving fluid layers within Earth, affecting its magnetic field. While we now know Earth isn't hollow in the literal sense Halley imagined, his intuition that Earth's interior is dynamic and layered wasn't entirely off the mark. Halley's hollow Earth theory inspired generations of writers and thinkers. Jules Verne's Journey to the Center of the Earth is perhaps the most famous literary exploration of this concept. Even as late as the early 20th century, some expedition proposals sought funding to find entrances to an inner world. While these fictional and pseudoscientific interpretations miss the mark scientifically, they reflect humanity's enduring fascination with what lies beneath our feet. Modern seismology has definitively disproven the hollow Earth theory, revealing instead a solid inner core, liquid outer core, and viscous mantle. Yet paradoxically, some aspects of Halley's speculations, particularly regarding fluid layers and their influence on Earth's magnetic field, contain kernels of truth that align with current understanding. The outer core is indeed fluid, and its movements generate Earth's magnetic field through a dynamo effect. The revelations about core leakage and lithospheric dripping give us a new perspective on these historical theories. While Earth isn't hollow, it's far more dynamic and interconnected than even modern geology textbooks typically portray. The boundaries between layers are zones of exchange rather than impermeable barriers. This brings us to a fascinating question. What else might be leaking from Earth's core? Helium-3 is just one tracer that scientists can measure, but it likely indicates a broader exchange of materials. The core is primarily composed of iron and nickel, but it also contains lighter elements, possibly including hydrogen, carbon, oxygen, silicon, and sulfur. If pathways exist for helium to escape, other elements might be making similar journeys. Some researchers speculate that this core-to-surface transport might play an unrecognized role in various geological phenomena. Could some volcanic systems be influenced by core-derived materials? Might certain mineral deposits have components that originated in the core? These questions are driving new research directions in geochemistry and geophysics. The study of Earth's core has practical implications beyond pure scientific curiosity. The core generates Earth's magnetic field, which shields us from harmful solar radiation and enables navigation. Understanding core dynamics helps scientists predict changes in this magnetic field, including the possibility of field reversals when north and south magnetic poles flip positions. There's also growing evidence that core processes influence surface climate over very long timescales. Heat flow from the core affects mantle convection, which in turn influences plate tectonics, volcanic activity, and ultimately atmospheric composition. The discovery of material exchange between core and surface adds a new dimension to these connections. What's particularly remarkable about these discoveries is that they're happening now, in the 21st century. We tend to think of Earth's basic structure as a settled question, but these findings show how much remains to be learned about our home planet. The tools of modern science, from high-precision mass spectrometers to supercomputer simulations, are revealing Earth's secrets that were previously inaccessible. These revelations also have implications for our understanding of other planets. If Earth's core leaks, might the same be true for Mars, Venus, or exoplanets around other stars? Comparative planetology is a growing field, and insights from Earth help scientists interpret observations of distant worlds. The story of Earth's leaking core reminds us that scientific understanding is never complete. Each discovery raises new questions and opens new avenues for exploration. The traditional model of Earth's layers as isolated systems is giving way to a more nuanced view of a planet in constant internal dialogue, with materials and influences flowing in multiple directions. This more dynamic view of Earth's interior also affects how we think about Earth's history and future. If materials from the core can reach the surface, they carry with them chemical and isotopic signatures from Earth's formation. These are like time capsules, preserving information about conditions in the early solar system. By studying these core-derived materials, scientists can piece together Earth's origin story in unprecedented detail. Looking forward, understanding core-mantle interactions helps scientists predict how Earth will evolve in the coming millions of years. Will the leakage of core materials accelerate or slow down? How might it affect Earth's magnetic field, volcanic activity, or even the movement of tectonic plates? These questions aren't just academic. They touch on the long-term habitability of our planet. The study of Earth's core also demonstrates the interconnectedness of scientific disciplines. What began as specialized research in isotope geochemistry has implications for seismology, plate tectonics, planetary formation, and even the search for habitable exoplanets. Science at its best transcends disciplinary boundaries, creating a more comprehensive understanding of natural phenomena. For the general public, discoveries about Earth's core offer something equally valuable: a sense of wonder. There's something profoundly humbling about realizing that the ground beneath our feet connects us to the earliest moments of Earth's formation. The atoms in that primordial helium have existed since the birth of our solar system, making an epic journey from the core to the surface, where human scientists can now detect their presence. This story also reminds us that Earth is not static but alive in a geological sense. From its molten heart to its rocky skin, our planet is in constant flux, growing, changing, and evolving. The timescales may be vast compared to human lifespans, but the processes are relentless. What appears solid and permanent to us is actually part of an ongoing planetary dance. As we consider these new discoveries about Earth's leaking core and dynamic interior, we're reminded of how recent our scientific understanding truly is. Modern plate tectonic theory is barely 60 years old. High-resolution seismic imaging of the deep Earth has only been possible for a few decades. Each generation of scientists builds upon previous knowledge, occasionally revolutionizing our understanding with new discoveries. What other secrets might Earth's core be hiding? What other assumptions about our planet might future research overturn? These questions keep geology vibrant and forward-looking, even when studying processes that have been underway for billions of years. In closing, the discovery that Earth's core is leaking material to the surface represents more than just an interesting scientific footnote. It's a fundamental shift in how we understand our planet's structure and evolution. It connects the air we breathe and the ground we walk on to the mysterious, inaccessible center of Earth. And it reminds us that even in an age of space exploration and quantum physics, some of the most profound discoveries await us right beneath our feet. The next time you pick up a volcanic rock or feel the ground shake during an earthquake, remember that you're experiencing the outer manifestations of Earth's restless interior. A dynamic system where even the deepest, most isolated parts of our planet find ways to make their presence known at the surface. Earth's story continues to be written, not just by external forces, but by the mysterious alchemy taking place thousands of kilometers beneath our feet.